Imagine looking up at the night sky. You see stars, planets, and galaxies glowing softly in the dark. But hidden among that beauty are regions where light itself disappears. Places so strange, so powerful, that they bend the very rules of reality. Astronomers call them black holes, but the name hardly does justice to the mystery. They aren't holes in the sense of gaps or tunnels, and they aren't truly black either. They are engines of gravity so strong that not even light can escape their pull. From the outside, they look like patches of nothingness, invisible shadows, but their influence reaches far beyond. For centuries, people wondered if such things could exist. The idea of a body so dense, so heavy, that nothing could get away from it was once just a thought experiment, dismissed as too extreme to be real. And yet we now know they are not only real, but common, lurking at the hearts of galaxies, born from the deaths of massive stars, merging, colliding, and shaping the universe in ways we are only beginning to understand. But here's the strange thing. Despite the name, black holes aren't just places where things disappear forever. They are dynamic, violent, creative. They sculpt galaxies, trigger explosions, and even whisper secrets about the very fabric of reality. To understand them is to glimpse how the universe truly works on its deepest, strangest levels. So tonight we're going to ask, what are black holes, really? How do they form? How do they behave? And why do they matter? And along the way, we'll find that they're not just cosmic destroyers, but also creators, architects, and storytellers written into the stars. Before we begin, let me ask you something. Where are you listening from right now? And what time is it where you are? Drop it in the comments. It's always incredible to see how far these stories travel across the world, how one night sky connects us all. Now, dim the lights, let your breathing slow, and imagine, far above you, a star collapsing, its light fading, its core falling inward into something so dense that the universe itself cannot let it go. What begins as a star's death will become the most mysterious object in existence. This is where the story of black holes begins. The words black hole might make you imagine a cosmic vacuum cleaner, sucking up everything in its path. A bottomless pit in space. A kind of galactic monster. It's a chilling image, and a misleading one. Black holes are not roaming predators, sweeping through the universe devouring stars at random. They don't chase planets or tear apart galaxies. In fact, if our sun was suddenly replaced by a black hole of the same mass, Earth would keep orbiting calmly, just as it does now. There would be no cosmic suction, no sudden destruction. The only difference would be that the warmth and light would vanish, leaving our world cold and dark. So if they aren't monsters, what are they? The simplest way to think of a black hole is as a region of space where gravity has gone beyond all limits. Imagine crushing an object smaller and smaller, packing its mass tighter and tighter. Normally, matter resists. Atoms push back, electrons repel, nuclei hold firm. But if you take a massive enough star and let it collapse after its fuel is spent, gravity wins. The star's core is compressed to a point where no known force can resist. That point is called a singularity. Around that singularity is the event horizon, the invisible boundary that separates the inside from the outside. Cross it, and escape is impossible. Not because you're being sucked in, but because the very geometry of space-time is tilted inward. To get away, you'd have to move faster than light, and nature doesn't allow that. So a black hole is not a hole in the way you might picture one in the ground. It's not a tunnel or a passageway to another place, though some theories imagine it could connect to a white hole or even another universe. Nor is it truly black, at least not from a distance. The space around a black hole can glow ferociously. As matter spirals inward, it heats up, sometimes shining brighter than an entire galaxy. Jets of energy can shoot out at nearly the speed of light, powered by the black hole's rotation. Paradoxically, the darkest objects in the universe are surrounded by some of the brightest displays. But the black hole itself, the region within the horizon, is hidden. No light, no information, no signal escapes from that interior. To us, it's as if reality ends at the edge. We can only see what happens just outside and infer the rest. That mystery, that invisibility, is what makes black holes both terrifying and fascinating. Think of it like this. If the universe is a great story written in light, then black holes are the pages that are missing, ripped out, forever unreadable. They sit there in the middle of the cosmos telling us there are things you cannot know. Not yet scientists have spent decades trying to strip away the myths. In the early 20th century, Einstein's theory of general relativity gave us the math that predicted them, though even he doubted they could exist. Later, as we peered deeper into the sky, we found evidence. Stars orbiting invisible companions, galaxies lit up by unseen engines, ripples in space-time from unseen collisions. Black holes went from speculation to reality, and yet the name itself still confuses. Black hole makes it sound like an absence, a void, when in fact it is the opposite. A concentration of matter so extreme that it bends space and time to breaking. A black hole is presence, not absence. Density, not emptiness. Gravity, made absolute. So when you hear the phrase, don't picture a hungry mouth swallowing stars. Picture instead a knot in the fabric of reality. A place where the rules change, where inside and outside no longer mean what they used to. And here's where the wonder comes in. Black holes are not exotic exceptions, they are common. At the heart of nearly every galaxy, including our own Milky Way, there lies a supermassive black hole. Millions or even billions of times heavier than the Sun. They are as much a part of the universe as stars and planets, woven into its structure from the beginning. So, what a black hole is and isn't matters. They are not cosmic monsters lurking to consume us. They are natural outcomes of gravity, the same force that holds the moon around Earth and Earth around the Sun. Push gravity far enough and you get a star. Push it to the extreme and you get a black hole. And while they are not hunters, they are powerful. They bend light into circles. They stretch time until it almost stops. They lock away information in ways that challenge our deepest understanding of physics. They are not holes, but laboratories, the ultimate testing grounds for the laws of nature. When we look at black holes this way, not as monsters but as mysteries, they become even more compelling. They are not here to frighten us. They are here to remind us how much we don't know, how much more there is to learn. And that is why the journey continues. If black holes are not cosmic vacuums, not bottomless pits, not predators in the dark, then what are they made of? What do they look like on the inside? How can something that seems to be nothing at all reshape the entire cosmos? The next step in our journey is to peel back that shadow and see how a black hole is built, from its horizon to its heart. To understand a black hole, you have to imagine peeling back layers of the most extreme object in the universe. From the outside, it looks like nothing more than darkness, an invisible sphere where light disappears. But if we could describe its structure, it would have three main parts: the event horizon, the singularity, and for many black holes, the furious disk of matter that swirls around them like a cosmic storm. Let's begin at the edge, the event horizon. Think of it as a boundary, but not one you could ever see. There are no signs, no shimmering wall, no glowing circle. It's an invisible threshold marking the point of no return. Once something crosses it, the rules change. Space itself bends inward so completely that all paths lead to the centre. To escape, you'd need to move faster than light, and nothing can. From far away, the event horizon looks like a dark sphere. Not a surface, not a shell, just the outline of where escape becomes impossible. If you fell toward it, you'd see the universe behind you warped into strange shapes. Light from stars would bend around the black hole, creating a halo, an eerie ring of distorted brightness. Astronomers call this the black hole's shadow, and it's the only reason we've ever been able to photograph one. But crossing the horizon is stranger still. To an outside observer, you'd never actually pass through. They would see you, slow down, freeze, and fade, your light stretched into longer and longer wavelengths until you vanish. To you, though, the fall would be seamless. You'd glide past the horizon without noticing anything unusual, unaware that you had entered a place no message can ever leave. Go deeper, and you reach the heart of the black hole, the singularity. Here, the equations of physics collapse. Mass is crushed into a point of infinite density, a place where space and time themselves cease to behave the way we understand. The singularity is where gravity overwhelms every other force, where atoms, particles, even the fabric of reality itself is pulled into something we cannot describe. And yet, though it sits at the centre, the singularity is not something you could ever see. It is hidden, forever cloaked by the horizon. What happens there is cut off from the rest of the universe. It is the ultimate secret, one that even Einstein's theory cannot explain. To probe it, we would need a theory that unites gravity and quantum physics, a theory we don't yet have. The singularity is not just a feature of black holes, it is a reminder of how incomplete our knowledge truly is. Now let's step back a little. Surrounding the black hole itself, outside the horizon, there is often a violent glowing structure, the accretion disk. Picture a whirlpool in space. Gas, dust, even whole stars can be caught in the black hole's gravity, swirling around it like water circling a drain. But unlike water, the matter in an accretion disk doesn't fall in quietly. It slams together at incredible speeds, heated to millions of degrees. The result is a furious ring of fire, a glowing disk that can outshine entire galaxies. Ironically, the darkest objects in the universe are often wrapped in the brightest displays of energy. From that disk, something even stranger can erupt. Relativistic jets. Thin beams of energy and particles shoot out from the poles of some black holes, stretching for thousands of light years. The exact mechanism is still debated, but the effect is clear. These jets can light up intergalactic space, sculpting entire galaxies with their power. Black holes may trap light inside, but they also unleash some of the most spectacular fireworks in the cosmos, and there's more. Just outside the event horizon, there is a zone scientists call the photon sphere. Here, light itself is forced into orbit. Imagine a ring of photons circling endlessly, trapped by gravity. If you stood there, impossible as that is, you could turn and see the back of your own head as your image wrapped around the black hole. This is where reality folds back on itself, where vision becomes a loop. Taken together, these pieces, the event horizon, the singularity, the accretion disk, the photon sphere, the jets, form the anatomy of a black hole. Each part plays a role in its mystery. The horizon marks the border, the singularity hides the truth, the disk and jets broadcast, the drama to the universe. But the most astonishing thing is how simple the black hole is compared to other objects. A star has layers, processes, fusions, magnetic storms, complex chemistry. A planet has geology, atmospheres, oceans, life. A black hole, in contrast, can be fully described by just three properties: its mass, its spin, and its electric charge. That's it. No matter what falls in, no matter how complex, all information is erased except those three numbers. This is known as the no-hair theorem, the idea that black holes are bald, stripped of detail. To the universe, a black hole that swallowed a star, a planet, or a cloud of gas is indistinguishable. Only the mass, spin, and charge remain. Everything else is lost. Or perhaps not lost, but hidden, locked behind the horizon in a way we cannot retrieve. This is the root of one of the greatest puzzles in physics. Does information truly vanish in a black hole, or does it somehow survive? That question is still unanswered. So the anatomy of a black hole is at once simple and impossibly complex. Simple in the sense that its structure can be broken into clean parts. Complex in that each part raises new questions. The horizon hides the singularity. The singularity defies explanation. The disk shines with deadly beauty. The jets stretch across galaxies, and yet the black hole remains silent. From the outside, it tells us almost nothing. We only see its shadow, its fingerprints on nearby stars, its ripples through space-time. The rest is imagination, inference and theory. Black holes are not monsters, not holes, not emptiness. They are knots in the fabric of the universe drawn tight by gravity, wrapped in layers of paradox. They are places where simplicity and mystery live side by side. And if we want to know where they come from, we have to look at their birth. The anatomy of a black hole tells us what it is now. But the next question is, how does such a thing come into being? Every black hole begins its story with a star that once shone brightly, fusing hydrogen into helium in its core, radiating warmth and light across the cosmos. For millions, sometimes billions of years, it lived in balance, gravity pulling inward, pressure from nuclear fusion pushing outward. But no balance lasts forever. Eventually the fuel runs low. For the largest stars, this is the beginning of the end. Their cores, once blazing furnaces, start to sputter. They fuse heavier and heavier elements in a desperate attempt to keep going. Helium into carbon, carbon into oxygen, oxygen into silicon, until finally, iron forms in the centre. And that is where the cycle stops. Iron cannot release energy through fusion. It only consumes it. With iron in the core, the star is doomed. Gravity, held back for so long, takes over. In seconds, the core collapses inward. Imagine the mass of a star tens of times heavier than our sun, crammed into a sphere no larger than a city. The pressure becomes so great that protons and electrons merge into neutrons, creating a neutron star. But if the star is massive enough, even neutrons cannot resist the crush. Gravity wins completely, and the collapse continues. The core shrinks past every limit until it becomes a singularity, the seed of a black hole. This violent collapse triggers one of the most spectacular events in the universe, a supernova. The outer layers of the star are blasted into space, shining brighter than entire galaxies for a brief time. The explosion scatters heavy elements, gold, uranium, calcium, oxygen, the very building blocks of planets, and life. And in the wreckage left behind, hidden inside the chaos, a black hole is born. That is the most common way a black hole forms, the death of a massive star. But it's not the only path. Some black holes may have formed in the earliest moments after the Big Bang. In those first fractions of a second, the universe was a seething ocean of energy and matter dense beyond imagination. Tiny fluctuations, ripples in that primal chaos, may have collapsed directly into what scientists call primordial black holes. If they exist, they could be as small as atoms or as heavy as mountains, drifting invisibly through space. We've never confirmed their existence, but if they are out there, they may help explain some of the deepest puzzles in cosmology, even the mystery of dark matter. There's another path too, direct collapse. Not all black holes are born from supernovae. In the young universe, enormous clouds of gas, thousands of times larger than stars, may have collapsed straight into black holes without ever igniting as stars first. This process could explain the presence of supermassive black holes, monsters millions or billions of times the sun's mass that sit at the centres of galaxies. How they grew so big, so fast, is still one of astronomy's great mysteries. Direct collapse may be one of the answers. Once a black hole exists, it can grow. Unlike stars, which burn fuel and eventually die, black holes only get larger. Every bit of matter that falls in, gas, dust, planets, even other stars, adds to its mass. Even black holes themselves can merge. When two galaxies collide, their central black holes can spiral together, merging into one larger black hole. These cosmic unions send ripples through space-time, gravitational waves, that race across the universe and can now be detected here on Earth. So black holes are not rare accidents. They are inevitable outcomes of cosmic evolution. Where there are massive stars, there will eventually be black holes. Where galaxies form, supermassive black holes seem to appear, anchoring their centres. Their birth is violent, but their existence is natural, woven into the fabric of how the universe works. And yet their origins raise haunting questions. How small can a black hole be? How large can one grow? Did the first black holes seed galaxies, or did galaxies form around them? Are primordial black holes still drifting through the cosmos unseen, tiny ghosts from the dawn of time? Each answer we find only seems to open more mysteries, but one thing is clear: black holes are not invaders. They are not cosmic outsiders. They are children of the stars, born in the same processes that give rise to light, planets, and life itself. They are the final stage of matter under gravity's rule. And that is what makes them so strange. Out of death comes something new. The collapse of a star gives birth to a black hole, which in turn can shape galaxies, trigger the birth of new stars, and even enrich the universe with the materials of life. Black holes are not just endpoints, they are beginnings too. So now that we've seen how black holes form, we can return to their variety. Not all black holes are the same. Some are small, just a few times the mass of the Sun. Others are unimaginably huge, sitting at the cores of galaxies, shaping the universe on scales we can barely grasp. Between them may lie intermediate giants, rare and difficult to detect. The next part of our journey will take us into this zoo of black holes, the stellar, the intermediate, and the supermassive. Each kind tells a different part of the story of how gravity sculpts the cosmos. Not all black holes are alike. Just as stars come in different sizes, from tiny red dwarfs to blazing blue giants, black holes too belong to a strange cosmic family with surprising variety. Some are small and elusive, hiding in the remnants of dead stars. Others are titanic monsters, anchoring entire galaxies. And in between lie a rare and mysterious middle kind that bridges the two extremes. Let's begin with the most familiar, stellar black holes. These are the children of stars. When a star much larger than our Sun dies in a collapse and supernova, the core left behind can form a black hole a few times to perhaps a few dozen times heavier than the Sun. They are scattered across the Milky Way, hidden in binary systems or drifting alone. We cannot see them directly, of course, but we know they are there by their gravitational fingerprints. Imagine watching a star orbit something invisible. The star wobbles, pulled by a companion that gives off no light. Or picture gas swirling in a glowing disk, heating up as it falls toward an unseen centre. Those are the telltale signs of stellar black holes, sprinkled quietly through our galaxy. Some are surprisingly close. Just a few thousand light-years away, Cygnus X1 is one of the best-studied stellar black holes discovered in the 1960s. For decades it has devoured gas from a nearby blue supergiant star, creating X-rays that reaches across space. That invisible shadow, that steady feast, was our first solid evidence that black holes truly exist. But stellar black holes are just the beginning. At the other end of the spectrum are the giants, supermassive black holes. These are the titans of the universe, weighing millions, sometimes billions, of times more than our Sun. They sit at the heart of nearly every galaxy we've studied, including our own Milky Way. Without them, galaxies might not even hold together. Our own galactic centre hosts a supermassive black hole called Sagittarius, a star. Though it is quiet now, it still commands the orbits of thousands of stars nearby. Astronomers have tracked those stars looping around an empty space, moving at breathtaking speeds, proving beyond doubt that something enormously heavy lurks there. Sagittarius, a star, is about 4 million times the Sun's mass, a giant compared to any star, yet modest compared to the true monsters out there. Take M87 star, the black hole whose image was captured in 2019 by the Event Horizon telescope. It sits at the centre of the galaxy Messier 87 and is 6.5 billion times the mass of the Sun. Its glowing ring of accretion gas was the first direct glimpse humanity ever had of a black hole's shadow. And then there are black holes even larger still, like the quasar engines from the early universe. Supermassive black holes so bright with feeding disks that they outshine the galaxies they live in. How these giants grew so quickly, so soon after the Big Bang, is still a mystery. Did they start as seeds of direct collapse? Did they merge and feed with extraordinary hunger? We don't yet know. Between the small and the gigantic lies a puzzle, the intermediate black holes. For years, scientists wondered if black holes existed in the middleweight range, hundreds or thousands of times the Sun's mass. These would be too big to be born from a single star, yet too small to anchor galaxies. They might form in dense star clusters, where repeated collisions of stars or smaller black holes eventually build up something larger. Evidence is rare, but hints exist. In 2020, gravitational wave detectors picked up signals from the merger of two black holes, producing one about 150 times the Sun's mass. It was the first solid proof of an intermediate black hole. Other candidates have been spotted lurking in dwarf galaxies or globular clusters, faint whispers of a population we're only beginning to uncover. Why does this middle group matter? Because they may hold the key to understanding how the giants formed. If intermediate black holes grew in the early universe, they could have been the stepping stones, the seeds that later became supermassive black holes. Without them, it's hard to explain how the titans we see today appeared so quickly in cosmic history. So the black hole family stretches across extremes. Stellar black holes just a few suns heavy, intermediate ones hundreds of suns, and supermassive black holes millions or billions of suns. From the death of stars to the birth of galaxies, black holes mark the stages of cosmic evolution. And yet, no matter the size, they share the same essence. Whether stellar, intermediate or supermassive, a black hole is defined by its event horizon. Horizon, its singularity, its irresistible gravity. The only differences are scale and context. A stellar black hole may quietly orbit with a companion star, feeding gently over time. A supermassive black hole may power a quasar, its jets blazing across space. But the fundamental reality is the same. It's humbling to think that the same physics governs both. The tiny black hole, a few times the mass of the Sun, and the behemoth in M87 are built on the same rules, just stretched to unimaginable scales. In the universe, size changes everything, but the underlying laws remain constant. So the question becomes, how do these black holes live out their lives? We've seen how they're born, in the death of stars, the collapse of clouds, or the merging of galaxies. We've seen their variety from the small to the colossal. But what do they do once they exist? Do they simply sit, waiting for matter to fall in? Or do they shape the cosmos in ways we can barely imagine? The answer lies in how they interact with their surroundings. For black holes may be silent on their own, but when paired with stars, galaxies, or gas, they become anything but quiet. Their feeding, their growth, their violent bursts of energy ripple across the universe, and that will be our next step. To explore what happens when matter dares to approach a black hole, and how the universe responds to their presence. For all their power, black holes are not constantly devouring everything around them. In fact, most of the time they are quiet, invisible, their presence betrayed only by the pull they exert on nearby stars. But when matter does drift too close, the silence ends. The black hole awakens, and what follows is one of the most spectacular, violent, and strangely beautiful displays in the universe. The process begins simply enough. A cloud of gas, a wandering star, or even the outer layers of a companion star might stray into the black hole's reach. Instead of falling straight in, the material begins to spiral, caught in the black hole's gravity. It orbits, faster and faster, closer and closer, until it forms a flattened whirlpool, the accretion disk. If you could see one, it would be dazzling. The gas in the disk doesn't just circle lazily. It slams together at enormous speeds, friction heating it to millions of degrees. The result is a ring of fire so bright it can outshine an entire galaxy. To distant telescopes, these disks are lighthouses in the dark, broadcasting the presence of an otherwise invisible object. Ironically, the most brilliant cosmic beacons are powered by things that swallow light itself. But the spectacle doesn't stop there. From some black holes, narrow beams of energy burst out from the poles, shooting across space at nearly the speed of light. These are the relativistic jets, among the most dramatic phenomena in the cosmos. Imagine a beam of matter and radiation so focused it can travel thousands, even millions of light years, punching through intergalactic space like a needle of fire. How can a black hole, which traps everything that crosses its horizon, produce such colossal outflows? That paradox is part of the mystery. The jets don't come from inside the horizon. Instead, they are launched by the magnetic fields and twisted space-time around the black hole, powered by the incredible energy of the swirling accretion disk and the spin of the black hole itself. Matter doesn't fall all the way in. Some of it is flung outward, focused into beams so powerful they can shape entire galaxies. Galaxies with active black holes at their centres are called active galactic nuclei, or AGN. When they're especially bright, they become quasars, objects so luminous that they can be seen across billions of light years. A single quasar, powered by a feeding black hole, can outshine all the stars in its host galaxy combined. In the early universe, quasars lit up the darkness, their jets and disks blazing like cosmic bonfires. Closer to home, the process is quieter but no less fascinating. In binary systems, where a black hole orbits a star, the black hole can siphon gas from its companion. The gas spirals into a miniature accretion disk glowing in X-rays before vanishing beyond the horizon. These systems flicker, flare and pulse as the black hole feeds. They are among the best laboratories we have for studying the physics of accretion and the strange behaviour of matter under extreme conditions. The feeding of a black hole is not a gentle meal. It is violent. Gas near the inner edge of the accretion disk moves at significant fractions of the speed of light. Temperatures soar high enough to strip atoms into plasma. Radiation floods out, powerful enough to sterilize whole regions of space. For anything nearby, a feasting black hole is not a neighbour to be desired, and yet paradoxically this violence can create. Jets from black holes can compress clouds of gas in galaxies, triggering the birth of new stars. The energy they release can regulate the growth of galaxies, preventing them from forming too many stars too quickly. Without black holes feeding and blasting energy into their surroundings, galaxies as we know them might not exist at all. So when we speak of a black hole feeding, we must picture both destruction and creation. Stars can be torn apart, their guts stretched and shredded into ribbons of light in events called tidal disruption events. Whole planets could be consumed without a trace, and yet the energy unleashed can seed new generations of stars, recycle matter into fresh forms, and sculpt galaxies into their graceful spirals and ellipses. In this sense, black holes are not just the endpoints of matter, they are engines of transformation. What falls into them may vanish, but before it does, it powers some of the brightest, most influential processes in the universe. Imagine watching it happen. A star wanders too close. Gravity stretches it, pulling harder on its near side than its far side until it is torn into a stream of gas. That stream whips around the black hole, forming a blazing disk. The disk glows hotter and hotter, a furious circle of light. Then, out of the poles, beams of radiation stab into space, carrying energy across intergalactic distances. In a cosmic instant, a quiet black hole becomes a blazing lighthouse, an object of awe and terror. And when the feast ends, silence returns. The jets fade. The disk cools. The black hole goes back to invisibility, waiting patiently for the next victim. The truth is, black holes don't seek food. They simply sit, waiting. Their power is passive, not active. They cannot choose, cannot hunt. But when something does stray into their grasp, the show that follows is unforgettable. So far we've explored what black holes are, how they form and how they feed. But perhaps the most mind-bending part of their story comes not from what they consume, but from what they do to the very fabric of reality. For black holes are not just massive objects, they are distorters of space and time themselves. Near their horizons, reality warps in ways that defy common sense. And so our journey now turns to what happens when you approach one of these beasts. What would you see? What would you feel? And what would time itself do as you cross the point of no return? Gravity is often described as a force, but Einstein showed us something deeper. Gravity is the bending of space and time themselves. Planets orbit stars not because they're tugged like stones on a string, but because the star curves the space around it, and the planets simply follow those curves. A black hole takes this bending to the extreme. It is not just an object with gravity, it is a place where space-time is distorted beyond recognition. To understand a black hole, you must imagine reality itself reshaped. Picture space as a stretched sheet of fabric. Place a marble on it, and the sheet dips gently. That's like the pull of Earth. Put a bowling ball on, and the dip is deeper, like the sun. Now imagine pressing down so hard the sheet rips into a funnel with no bottom. That's a black hole. The fabric of space doesn't just dip, it plunges into an abyss. This warping affects both space and time. Near a black hole, directions themselves are twisted. Normally you can move outward, away from an object's pull, if you have enough speed. But inside the event horizon, all possible directions point inward. Outward no longer exists as an option. Space itself has tilted toward the centre, and you're carried along with it. Time, too, slows down near a black hole. Not in the way waiting for an elevator feels slow, but in a literal, physical sense. Imagine watching a friend fall toward a black hole. To you, standing far away, their fall would look strange. They would seem to move slower and slower, their signals stretching into longer and longer wavelengths. Eventually, they would freeze at the edge, fading into invisibility. To you, they never crossed the horizon, but to them the story is different. Their own time feels normal. They fall straight in, cross the horizon without noticing anything special, and continue toward the singularity. Two truths exist at once. From outside, they never make it in. From inside, they fall without pause. This is the strange relativity of time at the edge of a black hole. Even light is not spared. Normally light travels in straight lines. Near a black hole, those lines are bent, twisted, even looped. The result is gravitational lensing. Stars and galaxies behind the black hole appear warped into arcs and rings. At the photon sphere, light can orbit endlessly, circling again and again before escaping or falling inward. For us, this creates one of the most haunting sights in astronomy, the glowing halo around a black hole's shadow. Light from the disk swirls and bends, wrapping around the hole before reaching us, creating a distorted ring. This is what we saw in the image of M87 star. Not the black hole itself, but the warped light around it, space-time twisted into a glowing outline. The warping doesn't stop with light, it stretches matter too. If you fell feet first into a stellar black hole, the pull on your feet would be far stronger than on your head. You'd be stretched thin, pulled like spaghetti, a process scientists call, with grim humour, spaghettification. For smaller black holes, this would happen outside the horizon, tearing you apart before you ever crossed. For supermassive black holes, the gradient is gentler. You could cross the horizon intact, only to meet your fate deeper inside. But perhaps the strangest effect is what black holes do to the idea of future. Normally you can choose where to go: forward, backward, sideways. Inside a black hole, the future itself is inward. Crossing the horizon is like stepping onto a slide you cannot climb back up. No matter what you do, every path leads to the singularity. It is not a choice. It is built into the geometry of time itself. All of this sounds alien, but it's not far away. In fact, the warping of space and time by black holes has been confirmed directly. When two black holes collide, they send ripples through space-time called gravitational waves. These ripples stretch and squeeze reality itself as they pass. In 2015, scientists detected such waves for the first time, a faint shiver in the fabric of existence from two black holes merging over 1 billion light-years away. The discovery was a triumph. It proved not only that black holes exist, but that their warping of space-time is real, measurable, and powerful. Every detection since has added another voice to the chorus of confirmation. The universe itself hums with the echoes of colliding black holes, and we can now listen. So when we talk about black holes, we are not speaking of distant monsters. We are speaking of the ultimate test of Einstein's theory, the purest expression of gravity's strange truth. They show us that space is not empty, and time is not absolute. Both are woven into a fabric that bends, twists, and even tears. And at the centre of a black hole, that fabric collapses. The singularity is not just a place where matter is crushed. It is a place where our understanding of reality itself fails. Space and time, as we know them, cease to make sense. That's why black holes are more than astronomical curiosities. They are laboratories. They force us to confront the limits of our knowledge, to ask whether the universe is stranger than even Einstein imagined. They connect the vast with the tiny, the cosmos with quantum physics. We began this journey with the idea of black holes as mysteries. Now we see they are not just dark voids. They are engines of distortion, bending space, stretching time, reshaping reality itself. But there is another layer still to uncover. If black holes bend space and time, what does that mean for the matter that falls in? What happens to the information, the history, the identity of what crosses the horizon? Is it lost forever, or somehow preserved in ways we don't yet understand? That puzzle, known as the information paradox, is one of the deepest questions in physics, and it will be our next step. Black holes are mysterious enough as they are, invisible, unstoppable, and built from the collapse of stars. But perhaps their strangest mystery is not what they swallow, but what they seem to erase. This puzzle is known as the information paradox, and it cuts right to the heart of physics itself. Let's start with something simple. In everyday life, information is never truly destroyed. Burn a book, and the words are gone in a practical sense, but the information is still there, scattered in the ash, the smoke, the rising heat. With enough knowledge, you could, in theory, reconstruct every letter. Physics insists on this. The universe keeps its books balanced. Matter and energy can change form, but the information about their arrangement always survives. Now consider a black hole. Toss in that same book. Toss in the fire, the smoke, the ashes. Toss in the entire library. To the outside world, all of it is gone. No light, no particle, no signal escapes once it passes the horizon. The only things we can know about the black hole are its mass, its spin, and its electric charge. Everything else, the details, the patterns, the stories, disappears. That is where the paradox begins. If black holes erase information, then the laws of physics as we know them break. Quantum mechanics, the foundation of modern science, insist that information cannot be destroyed. But black holes seem to do exactly that. For decades, this contradiction haunted physicists. It was Stephen Hawking who sharpened the paradox in the 1970s. He showed that black holes are not completely black. Through a subtle quantum effect near the horizon, they emit tiny amounts of radiation, now called Hawking. Radiation. Over immense timescales, this radiation allows a black hole to lose energy, shrink, and eventually vanish. But here's the catch. Hawking radiation appears to carry no information. It is random, thermal, like the glow of a hot stove. If a black hole eventually evaporates, all the information it swallowed seems to be gone forever, erased from the universe. That outcome breaks the most sacred rule of quantum theory. And so, the paradox was born. Some scientists argued that information is truly lost and that quantum theory must bend. Others argue that general relativity, our theory of gravity, must give way. Neither answer was satisfying, and for decades the debate raged. Ideas sprouted like stars in a nebula. Maybe the information is stored on the horizon itself, encoded somehow in its surface area. This led to the holographic principle. The idea that everything inside a black hole, maybe even everything in the universe, can be described by information painted on a boundary. It's as if reality itself might be a projection, like a hologram. Another proposal, maybe Hawking radiation is not entirely random. Perhaps, hidden in its subtle correlations, the lost information leaks back out, particle by particle in a cosmic trickle. If true, the black hole does not erase the past but whispers it back, incredibly slowly. And then there are wilder ideas still. Could black holes be gateways to other universes, sending information elsewhere instead of destroying it? Could they be connected to white holes, objects that spew out what black holes take in? These possibilities stretch imagination as much as science. What makes the paradox so powerful is not just that it's about black holes. It's about the deepest tension in physics, the clash between general relativity, which described gravity in the cosmos, and quantum mechanics, which describes particles in the microscopic world. Both theories work beautifully on their own, but when they meet at the edge of a black hole, they contradict each other. Something has to give. For physicists, this is both a nightmare and a dream. A nightmare because it shows that our two greatest theories cannot be the final word. A dream because solving the paradox might reveal the long-sought theory of everything, a framework that unites gravity and quantum physics once and for all. To this day, no one has a complete answer. The holographic principle has gained popularity, especially after discoveries in string theory. Some believe information is smeared across the horizon like ink on paper. Others point to quantum entanglement, suggesting that particles inside and outside the horizon remain mysteriously linked, allowing information to escape in disguised form. Whatever the truth, one thing is certain. Black holes are not just astronomical curiosities. They are thought experiments made real. They force us to confront questions about the very foundation of reality. Imagine standing at the edge of one, holding an object in your hands. You toss it in. To you, the object is gone. To the universe, what happened to that information? Did it vanish forever? Did it spread across the horizon? Did it leak back out in whispers of radiation? The black hole stands silent, giving no answers. And so, the paradox lingers, a cosmic riddle at the edge of knowledge. It is not just about what happens inside a black hole, but about whether the universe itself makes sense. Do the laws of physics keep their promises, or are there places where the rules break? Perhaps in the end, the information paradox is not a flaw but a clue, a sign pointing toward new physics, deeper truths, and a greater understanding of how reality works. Black holes swallow matter, light, and time. But maybe what they truly give us is insight, the chance to glimpse the limits of our knowledge and the possibility of something beyond. For now, we wait. We watch the sky, study the ripples of gravitational waves, trace the flickers of X-rays, and listen to the whispers of Hawking radiation. Each clue brings us closer, but the full answer remains hidden behind the horizon. And as we ponder the fate of information, we turn to another question. If black holes can evaporate through Hawking radiation, does that mean they are truly eternal? Or do even these cosmic giants eventually fade into nothingness, leaving behind not destruction, but silence? That question, the fate of black holes themselves, will guide us in the next chapter of our journey. For most of their lives, black holes seem eternal. They swallow matter, bend light, warp time, and then sit silently, impossible to destroy. To many, they appear as permanent fixtures of the cosmos, once born, never undone. But in the 1970s, Stephen Hawking made a startling discovery that changed everything. Black holes, he realised, are not truly immortal. They can, in fact, die. This revelation came not from telescopes, but from theory. Hawking combined Einstein's relativity with the strange rules of quantum mechanics. Near the event horizon, where gravity is strongest, quantum physics says the vacuum of space is never truly empty. Instead, pairs of virtual particles constantly pop into existence. One particle and its twin appearing from nothing, then annihilating each other in a blink. Normally, this dance leaves no trace, but near a black hole, something different can happen. If such a particle pair appears right at the horizon, one particle might fall in while the other escapes. To an outside observer, it looks as if the black hole is slowly emitting radiation. This faint glow, invisible to the eye but real in theory, is now called Hawking radiation. What does this mean? It means black holes are not completely black. They leak energy, and as they radiate, they lose mass. Over unimaginable timescales, they shrink. Slowly at first, then faster, until at last they evaporate completely, disappearing in a final burst of energy. The implications are staggering. Black holes, the great consumers of the universe, are also doomed to fade. Even the mightiest supermassive black holes, those weighing billions of suns, cannot last forever. Given enough time, far more than the current age of the universe, they will dissolve into radiation, leaving only cold, empty space behind. But Hawking radiation is not easy to grasp. It is unimaginably weak. For a stellar black hole, the radiation is colder than the cosmic microwave background that fills the universe. It's so faint we cannot detect it directly. Only tiny black holes, smaller than mountains, would evaporate quickly enough to produce noticeable heat, but we've never found any. For now, Hawking radiation remains a prediction, a whisper of theory waiting for confirmation. Still, its consequences ripple outward. If black holes evaporate, then information swallowed inside must go somewhere. Does it vanish? Does it return, hidden in the radiation? The paradox we explored before ties directly to this slow death. Hawking radiation is not just about black holes ending. It's about whether the universe keeps its secrets. Think about the timescales involved. A black hole the mass of the Sun would take about 10 to the power of 67 years to evaporate, a number so vast it defies comprehension. Supermassive black holes would take even longer, perhaps 100 billion years or more. By then, all stars will have burned out, galaxies will have faded, and the universe will be a dark, frozen place. The last sparks of light may come not from stars, but from the final moments of evaporating black holes. Imagine it, a universe billions of trillions of times older than today, silent and cold, dotted only with black holes slowly glowing away their existence. One by one they vanish, leaving nothing behind. The cosmos, once full of light and galaxies, ends in a quiet fade-out. This is the ultimate irony. Black holes, once thought to be eternal prisons, may be the last things to die. Their endings would mark the closing chapter of the universe's story. But here's where things grow even stranger. If black holes radiate and die, what happens at the very end? When the last stages of evaporation come, the process speeds up. The black hole shrinks faster, grows hotter, and emits more energy. Some theorists suggest it ends in a final flash, a burst of gamma rays that briefly lights up the darkness. Others argue it might dissolve smoothly, fading into nothing. Still others wonder if, at the last moment, hidden information bursts free, carried by the last sparks of radiation. We do not yet know, but the idea that black holes can end challenges our sense of permanence. The universe is a cycle of creation and destruction. Stars are born, they die, and they seed new generations. Black holes, too, are part of this cycle. Not eternal abysses, but temporary phases in the grand story of matter and energy. For Stephen Hawking, this discovery was both a triumph and a torment. It revealed a new truth about the universe, but deepened the paradox of information. If black holes evaporate completely, what becomes of the details of everything they swallowed? Does the universe erase its own history? Or is it written somehow into the radiation, encoded in ways we do not yet understand? This is why Hawking radiation is more than a theoretical curiosity. It is a doorway. It forces us to connect the largest scales of the cosmos with the smallest, gravity with quantum physics. It shows us that black holes are not just astronomical objects, but testing grounds for the very foundations of reality. As we stand at this point in our journey, we can see the full arc of a black hole's life. Born in the death of stars, they grow by feeding, warp space and time, challenge our laws of physics, and at last may evaporate into silence. Their story is one of extremes. Extremes of gravity, extremes of energy, extremes of thought. But the universe rarely leaves us with only one mystery. If black holes radiate and die, and if they may even burst in final flashes, could we see these events? Could we detect the death cries of ancient black holes? And what would they tell us about the fate of the universe itself? That brings us to the next step in our story, the possible role of black holes in the ultimate destiny of everything, the long, cold future of the cosmos. If black holes can evaporate, then they are not only actors in the story of the universe, they're also its final witnesses. Long after the stars have burned out, long after galaxies have grown dim and thin, black holes may remain as the last engines of energy. To imagine the fate of the universe is to imagine a cosmos shaped and eventually emptied by these dark giants. The timeline is vast beyond ordinary thought. Our own sun still has billions of years left to shine, but compared to the universe's potential future, that is only a blink. Fast forward trillions of years, and stars will have lived and died, galaxies will have aged, a new star formation will grind to a halt. The cosmos will dim, filled with the faint glow of red dwarfs and cooling remnants. Through it all, black holes will endure. Stellar black holes will drift like silent shadows, their parent stars long forgotten. At galactic centres, supermassive black holes will still spin, anchoring galaxies that have grown faint with age. Matter falling in will be rare, but their gravity will continue to shape the paths of stars for ages upon ages. Yet time is relentless. Even the most massive structures cannot resist its pull forever. Galaxies themselves will eventually disintegrate. Stars will wander, flung apart by gravitational interactions. Planetary systems will break apart. The universe will become a lonely sea, sparsely scattered with stars, remnants, and black holes. And still, the black holes will wait, patient, silent, heavy with the memory of what they consumed. For trillions of years, they will outlast everything else. Then Hawking's prediction takes over. One by one, black holes will begin to fade. The process is slow at first, so slow that for a supermassive black hole, it takes more years than the age of the universe multiplied beyond imagining. But time in the cosmos is infinite. Given enough of it, evaporation is inevitable. A stellar black hole will glow faintly as it shrinks, releasing particles into the emptiness. A supermassive black hole, billions of suns in weight, will shine faintly across unimaginable epochs, slowly dwindling. At the very end, each black hole will release its last burst of radiation, a final whisper of energy into a universe already gone cold. The picture this paints is bleak, but also strangely beautiful. Imagine the cosmos in that far-off future. No galaxies, no stars, no light except the fading sparks of evaporating black holes. A universe once blazing with creation reduced to silence, where the last events are the quiet deaths of the very objects once thought indestructible. Some physicists describe this as the heat death of the universe, the point when energy is so thinly spread that nothing new can happen. No more stars, no more growth, no more change, only darkness, stillness, and the cold glow of black holes finishing their work. And yet, the story may not be so simple. The fate of the universe depends not only on black holes but on the very nature of dark energy, the mysterious force driving cosmic expansion. If expansion continues to accelerate, galaxies will drift farther apart until no observer can see beyond their own island of stars. If dark energy grows stronger, even atoms could eventually be torn apart in a scenario called the Big Rip. In such a universe, black holes might not even get the chance to fade. They could be torn apart by the expansion of space-time itself. Other possibilities exist too. Some theories suggest the universe might one day collapse in a big crunch, reversing expansion and pulling everything, black holes included, back into a single dense state. Or perhaps the cosmos is cyclic, endlessly reborn, with black holes playing a role in seeding new universes through mechanisms we cannot yet imagine. But in the picture Hawking gave us, black holes are the closing act. They begin as the corpses of stars, grow into monsters that sculpt galaxies, and end as faint radiation that drifts away into the void. They are not eternal prisons but temporary chapters. In their birth, life; in their growth, violence; in their death, silence. It is humbling to think that the fate of everything, of galaxies, of stars, of the universe itself, might rest on these dark objects. They remind us that nothing lasts forever, not even the most powerful things we know. Time is patient, and given enough of it, time erases all. And yet, in that erasure lies a strange kind of continuity. The energy released by dying black holes will not vanish. It will spread into the cosmos, part of the endless exchange that began with the Big Bang. The universe will not end with a bang but with whispers, the slow fading of the very objects that once terrified and fascinated us. When we look at black holes this way, they stop being just curiosities of physics. They become markers of cosmic history. They are there at the death of stars, at the birth of galaxies, and perhaps at the end of the universe. They are the great bookends of existence, silent but essential. And for us, here and now, their story is more than just an abstract prediction. It is a reminder of impermanence, of the vast scales of time and space, and of the mystery still hidden in the laws of nature. We may never live to see a black hole evaporate, or the cosmos grow old, but by imagining it, we glimpse our place in something far larger. Even in their silence, black holes speak. They tell us that the universe is dynamic, fragile, and finite. That even the strongest forces give way to time, and that our search for understanding is only beginning. At first glance, black holes belong to the realm of the gigantic. They are born from stars, weigh as much as galaxies, and shape the architecture of the cosmos. Everything about them seems to belong to the scale of the very large, and yet, when we look closer, their greatest mysteries are hidden not in astronomy, but in the quantum world, the scale of the unimaginably small. This is where two great pillars of science collide. On one side is general relativity, Einstein's theory of gravity, which describes black holes perfectly well as curves in space-time. On the other side is quantum mechanics, which governs the dance of particles, fields, and energy at the smallest scales. Both theories are breathtakingly successful. Both have been tested again and again, And yet, at the centre of a black hole, they contradict each other. General relativity tells us that inside the horizon, all paths lead to the singularity, a point of infinite density. Quantum mechanics refuses to accept infinities. It insists that the world is granular, built from probabilities, particles, and limits. The singularity is where these two visions clash, where the smooth geometry of relativity breaks against the discrete randomness of quantum physics. The paradox is not only mathematical, it is philosophical. If the singularity is real, then the laws of physics as we know them end at the centre of a black hole. If quantum mechanics saves us from infinities, then perhaps the singularity is only an illusion, replaced by something stranger we do not yet have words for. This is why black holes are more than just astronomical curiosities. They are laboratories for new physics. Every time a star collapses, every time two black holes merge, the universe is testing itself at the edge of our knowledge. One path toward resolving this clash is the idea of quantum gravity, a theory that unites the cosmic and the microscopic. Candidates exist: string theory, loop quantum gravity, and others, each offering visions of space-time woven from fundamental building blocks. In these models, the singularity might not be a true point. Instead, it could be replaced by a dense knot of quantum structure, where gravity and particles merge into one description. From this perspective, a black hole is not a paradox but a window. By studying them, we might glimpse the rules of a universe deeper than either relativity or quantum mechanics alone can show. Hints of this connection have already surfaced. Hawking radiation itself is a quantum effect on a relativistic background, proof that black holes cannot be understood by one theory alone. The information paradox forces us to consider how quantum information behaves in curved space-time. Even gravitational waves rippling from colliding black holes carry whispers of physics at the edge of these two domains. Another idea lies in the holographic principle. Imagine that everything inside a region of space could be described not by its volume, but by the information on its surface. A black hole's entropy, the measure of its hidden information, seems to scale with its horizon's area, not its volume. This suggests that reality itself may work like a hologram. What happens in 3 dimensions might be encoded in 2. If true, this is not only about black holes, it is about the entire universe. We may live in a cosmos where the deepest truths are written on its boundaries. Quantum theory also brings us strange images of what a black hole might look like inside. Some propose that instead of a singularity, the core might be replaced by a ball of exotic matter, or a Planck star. Tiny, but unimaginably dense. Others suggest that black holes could be wormholes, shortcuts through space-time, stabilised by quantum effects. None of this is proven, but all of it shows the richness of ideas born from the meeting of quantum and gravity. What makes this meeting so haunting is its inevitability. We can study particles in labs and galaxies through telescopes, but black holes bring both scales together naturally. They are the crossroads where every theory must eventually pass. For now, we stand on the outside, listening. Our instruments catch the X-rays of accretion disks, the ripples of gravitational waves, the faint glow of distant quasars. But none of this reveals the interior. The horizon remains silent, keeping its secrets. To understand them, we need more than observation. We need new mathematics, new theories, perhaps even new ways of thinking about space and time. And yet, even without the full picture, one truth is already clear. Black holes do not simply destroy, they transform. They force us to connect the biggest and the smallest, the visible and the invisible. They are reminders that the universe is not divided neatly into categories, but is one whole waiting to be understood. The quantum world inside a black hole may never be accessible to us directly. No probe, no traveller, no light can escape to tell the story. But through theory, imagination, and the careful stitching together of physics, we can glimpse the outlines of what might be happening. And in those outlines lies the promise of something greater, a unification of knowledge, a deeper truth about what reality is. When we look up at the stars and imagine the black holes hidden among them, we are not only thinking about astronomy, we're thinking about the foundations of existence, about whether the universe is continuous or discrete, about whether information can vanish, about what happens when the laws of physics themselves are pushed to their breaking point. Black holes are the stage where the cosmic and the quantum meet, and in that meeting we may find not only the answers to their mysteries, but the answers to our own. When Einstein first unveiled his theory of general relativity in 1915, even he could not have imagined how far its predictions would reach. It was a theory about how mass bends space and time, explaining Mercury's orbit and predicting the bending of starlight during eclipses. But hidden in its equations were possibilities so extreme that Einstein himself doubted they could exist. Black holes were one of them. Today, a century later, black holes have become the ultimate testing ground for relativity. Nowhere else in the universe is gravity pushed so far, so violently, so cleanly. To study them is to test Einstein's theory at its limits and to see if it holds. The first test came from the stars. In the centre of our own Milky Way, astronomers observed stars whipping around an invisible point, moving at thousands of kilometres per second. Decades of careful observation revealed orbits so tight, so precise, that nothing but a supermassive black hole could explain them. Relativity said this should be possible, and nature agreed. Then came the light. General relativity predicts that gravity bends light, not just the path of planets. Near a black hole, this bending becomes dramatic. Light from stars behind it curves into arcs and halos, an effect we call gravitational lensing. In 2019, this prediction was captured directly. The Event Horizon Telescope stitched together data from around the world to produce the first image of a black hole's shadow, the glowing halo of bent light around M87 star. It was a moment Einstein might have found both shocking and inevitable. But the most spectacular confirmation came not from light, but from vibrations in space-time itself. When two black holes spiral together, their collision sends ripples outward, gravitational waves. Relativity predicted them, but for a century they remained undetected, too faint for our instruments. That changed in 2015, when LIGO heard the universe hum for the first time. Two black holes, 1.3 billion light-years away, merged in silence, but their waves reached us across time and space. It was as if the universe whispered, directly into our instruments, relativity is real. Since then, dozens of collisions have been recorded, each one a fresh test of Einstein's theory under conditions impossible to recreate on Earth. Each detection has matched his equations almost perfectly. And yet, the more we test relativity with black holes, the more we search for cracks. Because if there are cracks, tiny deviations from prediction, they could point to new physics. Theories that unify gravity with quantum mechanics may reveal themselves in the smallest imperfections. So far, relativity is not broken. The shadows we see, the waves we detect, the orbits we track, all fit within its framework. Black holes are Einstein's triumph, proof that his vision of gravity holds even at the edge of reality. But there are mysteries still. Relativity describes the geometry of black holes flawlessly, but it cannot tell us what happens at the singularity. It cannot resolve the information paradox, it cannot explain how black holes evaporate, it cannot merge smoothly with quantum mechanics. In this way, black holes are not only confirmations of relativity, but also its greatest challenge. They show both its strength and its incompleteness. They say, this theory works, but it is not the final word. Consider what it means that we can now listen to the universe through gravitational waves. Every ripple is a fingerprint of space-time in motion. Every detection is a new opportunity to test relativity against reality. Already, some events hint at the unknown. Black holes larger than expected, collisions stranger than models predicted. Perhaps hidden in this data are the first signs that Einstein's masterpiece will someday give way to something deeper. Black holes also test relativity in more subtle ways. The time dilation near their horizons is not just a thought experiment, it has been measured. Light from matter near a black hole is stretched, reddened, slowed, exactly as relativity demands. Even the way black holes spin, dragging space-time around them like syrup stirred with a spoon, has been confirmed by X-ray observations. Every test so far has strengthened the theory, but every test also sharpens the question: when will we find the place where relativity bends, not space-time, but itself? Perhaps the answer lies not in observation, but in the very existence of singularities. Relativity allows them but cannot explain them. They are the silent admission that the theory is incomplete. A singularity is not just a dot in space. It is a marker saying, beyond here, new laws are needed. In this way, black holes are both the crown jewel of Einstein's work and the signpost toward its successor. They show us how gravity rules the cosmos, how space-time itself can curve into darkness, and how predictions made a century ago still hold true. But they also stand as puzzles, daring us to imagine a framework where quantum and relativity unite. When we look at a black hole, we are not only seeing Einstein's equations made real, we are seeing the limits of human knowledge. We are seeing the boundary between what we understand and what remains hidden. Black holes confirm the past and beckon toward the future. In the end, relativity passes every test we can throw at it. But black holes remind us there are greater tests still to come. When Albert Einstein published his general theory of relativity in 1915, he was not thinking about cosmic abysses that swallow light. His goal was simpler: to explain how gravity worked. He showed that space and time are not rigid backdrops, but flexible, woven together like fabric, bending under the weight of matter. Planets follow curved paths not because they are tugged by an invisible force, but because space itself is bent. It was revolutionary and unsettling. The math implied something so extreme that even Einstein doubted it could exist. Objects so dense that they would carve space into pits so deep that nothing could escape. The first hints of black holes were buried in the equations from the start. But for decades they were seen as mathematical curiosities, not physical realities. A century later, black holes are no longer speculation. They are the ultimate testing ground of relativity. Every observation of them, every ripple of energy they send across the cosmos, is a chance to see if Einstein's vision still holds when pushed to the absolute limit. One of the clearest tests comes from the centre of our galaxy. For more than 30 years, astronomers have tracked the orbits of stars near Sagittarius A star, the supermassive black hole at the heart of the Milky Way. These stars move at blistering speeds, slingshotting around an unseen centre. Their paths trace invisible curves, just as relativity predicts. Watching them is like watching Einstein's equations written directly into the sky. Another test lies in light itself. Relativity predicts that gravity bends light, and nowhere is this bending stronger than near a black hole. Distant stars behind it should appear warped, smeared into arcs and rings. In 2019, this prediction became an image. The Event Horizon Telescope revealed the shadow of the black hole in the galaxy M87. A glowing halo of gas, twisted light bent around darkness. It was the first time humanity had looked directly at the edge of a black hole, and Einstein's theory fit the picture almost perfectly. But perhaps the most dramatic confirmation came from soundless vibrations in space-time, gravitational waves. When two black holes spiral together and collide, they send ripples through the universe itself. Relativity predicted these ripples, but for a century they remained undetectable. Then, in 2015, laser observatories on Earth finally caught the faint stretching of space as two black holes merged over 1 billion light-years away. For a fraction of a second, the event released more energy than all the stars in the observable universe combined. That whisper, captured across cosmic distance, was a triumph of Einstein's theory. Since then, dozens more mergers have been detected. Each one is a test, comparing the waveforms against relativity's predictions. Again and again, the matches are nearly perfect. Einstein's equations, written on paper 100 years ago, still describe the dance of black holes colliding in the farthest reaches of the universe. Yet these triumphs come with a shadow. The closer we look, the more we see the edges of what relativity can explain. It handles the horizons, the orbits, the bending of light, the rippling of space-time. But when we ask what lies at the singularity, the very heart of the black hole, the theory falls silent. Relativity predicts infinities, points of zero size and infinite density. Physics cannot accept this. Somewhere in that silence, relativity must give way. This is why black holes are not just confirmations of Einstein's genius, but also warnings that his theory is incomplete. They mark the border between what we know and what we cannot yet explain. General relativity and quantum mechanics, our two greatest achievements, clash violently at the singularity. Somewhere in that clash lies the key to a deeper theory, one that unites the very large with the very small. Even before that ultimate frontier, black holes push relativity into strange territory. They drag space itself when they spin, twisting it like a spoon in syrup. They slow time so drastically that an hour near the horizon could mean centuries outside. They bend light so completely that you can see behind them, orbits wrapping into impossible loops. Every one of these effects has been measured, confirmed, and matched to Einstein's predictions. And yet scientists search relentlessly for cracks. Perhaps tiny deviations will appear in the patterns of gravitational waves. Perhaps the shadows we photograph will reveal subtleties Einstein's theory cannot explain. If those cracks exist, they could lead to something new. A bridge between relativity and quantum theory. A step toward understanding the true fabric of reality. For now, relativity continues to hold. The shadows match. The waves ring true. The orbits align. Black holes, once the most unlikely prediction of Einstein's math, have become his strongest vindication. They prove not only that space and time are flexible, but that his equations can survive at the very brink of physical possibility. Still, the singularity waits. The paradox of information remains. The marriage of relativity and quantum mechanics has yet to be written. Black holes show us Einstein's brilliance, but they also show us his limits. They are both a monument to what we have discovered and a gateway to what we have yet to learn. When we study black holes, we're not just testing equations. We're asking whether the universe itself is fully knowable, or whether there are truths that remain hidden behind horizons. Relativity passes every trial, but in the heart of a black hole, the next revolution is waiting. For much of their existence, black holes are quiet. They sit in darkness, pulling on nearby stars, drifting through galaxies, waiting. But when they meet each other, silence ends. Their collisions are some of the most violent events the universe has ever known. Cosmic symphonies played not in light, but in gravity itself. Picture two black holes locked in orbit. Perhaps they were once massive stars born as a pair, living side by side until both collapsed. Perhaps they were drawn together when their galaxies collided, spiraling slowly toward each other over billions of years. Whatever their origin, their dance begins far apart, graceful and slow. Each orbit carries away a tiny bit of energy in the form of gravitational waves, ripples in the fabric of space-time. Those waves are faint at first, weaker than the movement of an atom, but as the black holes spiral closer, the waves grow stronger, the orbit tightens, the dance quickens, they circle each other hundreds of times a second, space itself ringing with their motion. At the end, the two horizons touch. In a fraction of a second, they merge, forming a single, larger black hole. A final burst of gravitational waves surges outward, carrying more energy than all the stars in the universe shine in that moment. This is not light. It is not sound. It is the stretching and squeezing of reality itself, a vibration in space-time. When detectors on Earth first captured such a signal in 2015, it was the faintest of whispers, a tiny quiver in miles-long laser beams. Yet that whisper carried the story of two black holes colliding over 1 billion years ago. Humanity had finally heard the universe speak in gravity's voice. Since then, dozens of these collisions have been recorded. Each one has its own character. Some involve small stellar black holes, 10 or 20 times the mass of the Sun. Others involve heavier partners, 30, 40, even more. In rare cases, collisions have created black holes of unexpected size, hinting that we are only beginning to understand the variety of these cosmic unions. The violence of these events is hard to imagine. In the final seconds before merger, the black holes move at half the speed of light. They curve space-time so strongly that time itself distorts. The waves they send out ripple across billions of light years, undiminished until they reach us. For a brief instant, they outshine every other source of energy in the observable universe, and then they vanish, leaving behind silence and a larger, calmer black hole. Collisions are not limited to stellar black holes. At the centres of galaxies, supermassive black holes also meet. When galaxies merge, a common fate in cosmic history, their central giants sink toward one another. For millions of years they circle in a slow, inexorable dance, pulling on stars, stirring up gas, warping their galaxies' shapes. Eventually they too collide, releasing waves so vast that they stretch across the universe. We have not yet directly detected such supermassive mergers, but the evidence is all around us. Pairs of bright quasars, dual jets, and disturbed galactic centres hint at black holes preparing to meet. In the coming decades, new detectors in space sensitive to lower frequencies may capture their deep, slow waves. When that happens, we will hear not just the whispers of stellar collisions, but the deep bass notes of giants merging at the hearts of galaxies. These events are more than cosmic spectacles. They shape the universe. Mergers build bigger black holes, feeding the growth of the monsters that anchor galaxies. The waves they release carry information about space-time itself, testing relativity under conditions we cannot recreate anywhere else. Each collision is both an ending and a beginning, the death of two black holes, the birth of one new one. And sometimes, the violence leaves scars we can see. When a collision is uneven, when one black hole is much larger than the other, the merged remnant can be kicked away, flung through space at thousands of kilometers per second. Astronomers have found galaxies with their central black holes missing, or streaking outward like cosmic runaways. Even the mightiest anchors of galaxies can be shaken loose by the violence of their own unions. The story of black hole collisions is also a story of patience. These dances take eons to complete. From the first slow spirals to the final crash can span millions or billions of years. We see only the last heartbeat, the instant of climax. But in that heartbeat lies the history of galaxies, stars, and the deep evolution of the cosmos. Imagine watching two such giants collide. At first, nothing would be visible. The black holes themselves are dark. Slowly, their motions stir nearby gas into turbulence, igniting jets and flares. Stars scatter from their orbits. As the horizons draw near, space twists, time stretches, and the whole region becomes a storm of invisible waves. Then, in less than the blink of an eye, the two become one. A final surge of energy blasts outward, and then, calm. The new black hole settles into stillness, its horizons ringing like a bell before fading into silence. These violent lives remind us that black holes are not only solitary graves of stars, they are participants in the drama of the universe, meeting, merging, reshaping themselves and the galaxies they inhabit. Their collisions are both destructive and creative, breaking apart old structures while forging new ones. Every detection we make brings us closer to understanding their role. The faint ripples in our detectors tell us not only about the black holes themselves, but about the fabric of reality. They confirm Einstein's equations, challenge our theories, and give us a glimpse of processes too vast to imagine otherwise. And even as we listen to these cosmic mergers, questions remain. How many black holes are wandering alone, the products of kicks from violent unions? How often do galaxies collide? And what does that mean for the giants at their centres? Could collisions create entirely new phenomena we have yet to recognise? What we do know is that the universe is filled with them. Somewhere, right now, two black holes are circling each other, their waves already spreading outward. They will reach us in millions or billions of years, a story carried in silence across time. When we think of black holes, we often picture stillness, emptiness, silence. But their lives can be anything but quiet. Their collisions are the loudest events in the universe, not in sound, but in the vibration of existence itself. Galaxies may look serene from afar, soft spirals of light, delicate swirls of dust, or giant glowing ellipses hanging in the dark. But hidden at their hearts, black holes are quietly shaping everything we see. These dark centres are not just passengers in galaxies. They are architects, influencing the birth of stars, the growth of structure, and the very balance of the universe. Nearly every large galaxy we've studied holds a supermassive black hole at its core. Their masses vary wildly, from millions to billions of suns. Our own Milky Way shelters one about 4 million times the Sun's mass. The giant in Messier 87 tips the scales at 6.5 billion suns. Even dwarf galaxies, fragile and small, often hide central black holes of surprising heft. At first glance, it seems impossible that something so compact could matter on galactic scales. After all, even a supermassive black hole is tiny compared to its host. If the Milky Way were the size of North America, Sagittarius, a star, would be smaller than a grain of sand in the centre. How could such a small thing govern a galaxy stretching 100,000 light years? The answer lies in energy. When gas falls into a supermassive black hole, it does not simply vanish. It heats, glows, and blasts radiation across space. The accretion disks around active black holes are among the most luminous engines in the universe, outshining every star in their galaxy. The jets they produce, thin beams of plasma accelerated nearly to light speed, can travel hundreds of thousands of light years, stabbing through intergalactic space. These outbursts are not just spectacular, they are transformative. When a black hole feeds, it pours energy back into its surroundings. That energy stirs up clouds of gas, preventing them from cooling and collapsing into new stars. In other regions, it compresses clouds, sparking starbirth in sudden bursts. In this way, black holes regulate their galaxies like thermostats, keeping star formation from running too hot or too cold. Without this balance, galaxies might collapse into chaos or burn through their fuel too quickly. Astronomers call this feedback the push and pull between black holes and their galaxies. Observations show that the mass of the galaxy's central black hole is tightly linked to the mass of its bulge, the dense cluster of stars in its centre. This is the M-sigma relation, a correlation so consistent it suggests black holes and galaxies grow together. A bigger galaxy means a bigger black hole, and a bigger black hole keeps its galaxy in check. The story goes back to the early universe. Just a few 100 million years after the Big Bang, young galaxies were chaotic, colliding and merging in a frenzy of growth. Their black holes too were young, feeding greedily on the torrents of gas around them. Some became quasars, blazing with such intensity that we can still see them billions of years later. These early giants shaped the galaxies they lived in, deciding how many stars would form, how much gas would remain, and how structure would evolve. Even today we see their fingerprints. The jets of active black holes sculpt galaxies into strange shapes. Entire cavities have been carved into clusters of galaxies by the force of those outflows. The delicate balance between feeding black holes and cooling gas determines whether galaxies remain fertile with star birth or fade into quiet collections of old stars. Black holes also play roles as anchors. In the bustling centres of galaxies, stars move at tremendous speeds, whipping around invisible points. Without the gravity of a central black hole, many galaxies would not hold their shape. They would dissolve, their cores unstable. The black hole's presence, small though it is in size, acts as a gravitational keystone. This influence stretches even farther. When galaxies collide, and they often do, their black holes are dragged toward each other. Eventually they merge, unleashing gravitational waves and reshaping their galaxies once more. These unions may explain why the largest galaxies hold the largest black holes. Growth on one scale feeds growth on the other, bound together in cosmic evolution. It is humbling to realise that the stars we see in the night sky owe their history, in part, to a hidden monster in the centre of our galaxy, Sagittarius. A star is quiet now, feeding only occasionally on stray gas clouds. But in the past it likely blazed as an active nucleus, pouring energy into the Milky Way, regulating how stars formed, and perhaps even shaping the conditions for life on Earth. The role of black holes as architects is not one of destruction, but of balance. They are not reckless destroyers, they are regulators. Without them, galaxies might look very different. Perhaps brighter, but shorter-lived. With them, galaxies grow steadily, evolve gracefully, and last for billions of years. Even as they sit silent, their influence lingers. The Milky Way turns in calm spirals, its stars orbiting peacefully, its gas forming new generations of suns. And at the centre, hidden behind clouds of dust, Sagittarius, a star, keeps its quiet watch. From the smallest dwarf galaxies to the most massive clusters, the story is the same. Black holes shape galaxies, and galaxies shape black holes. They are not separate players, but partners in the grand design. The universe we see, its spirals, its clusters, its patterns of light, has been sculpted in no small part by the darkness at its heart. The story of black holes is not only about darkness and endings. Paradoxically, it is also about creation. For while black holes themselves swallow matter, the violence that surrounds them is responsible for forging many of the elements that make up the universe, and us. Every atom in your body has a history. Hydrogen, the simplest, was born in the Big Bang. Carbon, oxygen, and nitrogen were created in the cores of stars. But the heavier elements, gold in your jewellery, uranium in the Earth's crust, even the calcium in your bones, required events of extraordinary violence, and among the most important of those events are the deaths and collisions of massive stars that give rise to black holes. When a star many times the mass of the Sun reaches the end of its life, its core collapses into a black hole or neutron star. The collapse triggers a supernova explosion, blasting the outer layers into space at astonishing speeds. In that instant, the heat and pressure soar high enough to fuse elements heavier than iron. The explosion scatters them into the galaxy, seeding the raw material for planets, oceans, and life. Without the deaths that create black holes, the universe would be a simpler, poorer place. But the story doesn't end there. In recent years, scientists have discovered that some of the heaviest elements come from even rarer events, the collisions of neutron stars and black holes. When two neutron stars spiral together, the energy released is almost unimaginable. The collision squeezes matter into conditions so extreme that it forges gold, platinum, and other heavy elements in vast quantities. For the first time in 2017, astronomers observed such a merger directly. Telescopes across the world caught the light of the explosion, while gravitational wave detectors captured the ripples in space-time. In that moment, humanity saw the birth of elements in real time. Black holes themselves also play a role. When a neutron star collides with a black hole, much of its matter is torn apart before crossing the horizon. That shredded matter, briefly free, undergoes nuclear reactions that create heavy elements, later scattered into space. Even the feeding of black holes through their accretion disks contributes to cosmic chemistry. The heat and pressure in those disks drive nuclear processes and unleash winds that spread enriched material far beyond the black hole's reach. It is a strange irony. Black holes, symbols of destruction, are also midwives of creation. They help distribute the building blocks of worlds. Without them, there might be no rocky planets, no mountains of iron, no seas of water, no creatures to wonder at the night sky. Think of the gold ring on a finger. Somewhere in the distant past, long before, Earth formed, two massive stars collapsed, their cores becoming black holes or neutron stars. Perhaps those remnants spiraled together, colliding in a flash so bright it briefly outshone their galaxy. In that collision, atoms of gold were born. Billions of years later, scattered across interstellar dust, they joined the cloud that formed our solar system. They became part of Earth and eventually part of us. Every heavy element we touch carries a memory of violence, written in the physics of black holes. This cycle ties death to life, destruction to creation. A star dies, leaving behind a black hole. Its explosion sows the elements of new generations of stars and planets. Black holes collide, spreading still more riches. Out of collapse comes abundance. The influence is not only chemical but structural. By distributing heavy elements, black hole events change the cooling properties of gas clouds, making it easier for them to collapse into new stars. They enrich galaxies, allowing complexity to flourish. Even life depends on this cycle. No supernova, no carbon, no mergers, no gold, no black holes, no Earth as we know it. In this way, black holes are silent participants in our own existence. The iron in our blood once passed through a star that collapsed. The calcium in our bones may have been forged in the fire of a supernova. The heaviest elements that shape our world were likely born in the aftermath of collisions tied to black holes. It is a reminder that the universe is not simply destruction or creation, but both at once. Black holes consume, but the processes around them enrich. They take, but they also give. They are cosmic recyclers, driving the endless exchange of matter from one form to another. When we look at the periodic table, we are looking at a map of cosmic history. Each element tells a story of birth and death, of stars collapsing and black holes forming, of collisions shaking galaxies. Our own bodies are archives of those stories, built from atoms forged in the chaos black holes leave behind. So, the next time you hear of black holes described only as cosmic monsters, remember this other truth. They are also creators, shapers, givers. Their violence is our inheritance. Their darkness made our light possible.